Section 4.3 is about factoring, or the introduction to factoring of polynomials. But before we talk about factoring polynomials, I just want to make some general comments about factoring of integers and what that means. For example, when we have a number like 6, we can write that number as a product of two factors, 2 times 3. So you have seen that before, and that's no surprise. And in fact, that was also covered on page 17 in the beginning of the book, and please review that, page 17. And then there's something called prime factorization of an integer. So you can take maybe the number 150. And so obviously you can write that as a product of 10 times 15. That would be an easy way of factoring that. But each factor, 10 and 15, can be factored again. 10 could be written as 2 times 5. And 15 could be written as 3 times 5. So these are then the prime factors of 150. We can write it as 2 times 3 times 5 times 5, or more commonly it's written as 2 times 3 times 5 squared. And that is the prime factorization of 150. And it doesn't matter how you start, in the end it's the same factorization. It's called a prime factorization because every factor is a prime number. And the idea of factoring polynomials is really the same way. We want to factor polynomials, so the polynomial that's written as the sum of terms can now be expressed as a product of terms. And there are many reasons for why that's an important matter. So we also want to do the prime factorization of polynomials. So that's kind of the end game here eventually, that we factor polynomials so that at the end we have a product of prime polynomials. And as there are numbers that cannot be factored, like 17, so 17 is a prime number. There are many more prime numbers, of course. In fact, there are infinitely many. But prime numbers are pretty important in many ways, and not to get into that right now. But in the same way, they're prime polynomials. They're polynomials of more than 2 or 3 terms that cannot be factored over the integers. So just a heads up on that. So the objectives here in section 4.3 is to factor polynomials whose terms have a common factor, and factor certain polynomials with 4 terms by grouping. Now that part, factoring by grouping, is really, really important. So the B part is something you really want to pay a lot of attention to, and the A part is relatively straightforward. Here are some important basic definitions about factoring and factorizations. The factor polynomial is to express the polynomial, a sum of terms, as a product. And a factor of a polynomial p is a polynomial that can be used to express p, the polynomial, as a product. And a factorization of a polynomial p is an expression that names p as a product of factors. We're talking about a product of factors. And so first of all, we're looking at terms with common factors. And the first example is 2y minus 2. And at this point, I'd like to direct your attention to page 22 in the beginning of the book. And you look at that. There are examples how to factor things of that nature. So here, the common factors are the number 2. And it becomes more obvious when we write this as 2 times y minus 2 times 1. Or better yet, 2 times y plus 2 times minus 1. So now we see that 2 is a common factor. And as it was explained on page 22 in the book, we can write this as 2 times y minus 1. And the minus 1 is really important. It's like a placeholder. And you can confirm that this is a correct factorization by using the distributive law. 2 times y is 2y. That's what we started out with. And 2 times minus 1 is minus 2. So that would be the correct factorization. And when we look at example number 2, the best thing to do is to look at the coefficients first and see if there's a common factor among the coefficients. And when you look at 15 and 10 and 5, you notice that 5 is a common factor among all of these terms. So we can write this as, let's say, 5 times 3y plus 5 times minus 2y, and we can write this as 5 times 5. So then we can take the common factor of 5 from each term, right in front of the parentheses. So that means then 5 times 3y minus 2y plus 5. And again, you can confirm that this is the correct answer by using the distributive law or distributive property and say 5 times 3y is 15y, and 5 times minus 2y or rather x, sorry about that, this was an x. And 5 times minus 2x is minus 10x, and 5 times 5 is 25. So that's why we can say that is the correct answer. 3y minus 2x plus 5. And here's another example. 20x to the fourth minus 5x to the third. So here, when you look at the coefficients, 5 is certainly a common factor. So we have 5 and a 5 here. But now we also have x as a common factor, and we always choose the lowest power of the variable, in this case x to the third, as the factor we can factor out. So this then becomes 5x to the third, and times 4x, that would give us a 20 x to the fourth, right? 5 times 4 is 20, and x to the third times x is x to the fourth. And then minus 5x to the third times 1. So we need the 1 here as a placeholder for sure. So now we can write this as 5x to the third in front of the parentheses that now include 4x, and the minus sign goes over to the 1, minus 1. And again, you can verify that this is correct by using the distributive law to multiply 5x to the third times 4x. 5 times 4 is 20, and x to the third times x is x to the fourth. And 5x to the third times minus 1 is minus 5x to the third. When you look at example number 3, we look at the coefficients and we find 12 and 20 have a common factor of 4. So there would be a factor of 4. Then we notice x is common to both terms. And the lowest power of x is 2, so we use x squared. And then there's a y factor in each one of these terms, so we factor 4x squared y. And so that leaves us a 3, because 3 times 4 is 12, x squared y. And here, when we factor 20 by 4, that's 4 times 5, so that's a 5. And there's an x left over, because then x squared times x gives us an x to the third. So that would be the factorization of the polynomial to the left. a monomial times a binomial. Again, we had this before, a monomial times a binomial, as we had it in the previous examples also. Okay, so now let's do some factoring here, some very simple little exercises. And the first one says factor 3x squared minus 6. Well, so we have 3x squared minus 6. And we know we can write 6 as 3 times 2. So we notice that 3 is a common factor. And since there's no x in the second term, we cannot factor out an x, but we can factor out a 3. So 3, and then there's an x squared, and there's a minus 2. And so that would be the factorization of the polynomial, monomial times binomial. And again, we check our answer, our work. 3 times x squared is 3x squared, and 3 times minus 2 is minus 6. So this is our correct answer. And when we look at example number 2, we notice that among the coefficients, 4 and 8, the greatest common factor is 4. I mean, there are other common factors, like 2 and 1, but we want the greatest common factor that we can factor out. And 4 is the greatest common factor. And then the x is in each term, but the lowest power of x is 3, so we can factor 4x to the third. And that means we have an x squared left over here, an x to the third. That's a 3. So we have an x squared. And there would be a negative 2. Because 4x to the third times x squared is 4x to the fifth. And 4x to the third times minus 2 is minus 8x to the third. So in number 3, it gets progressively more complicated, a little longer at least. So let me rewrite this for you. It makes it a little bit easier. So we look at the coefficients, and we notice that 3 is the greatest common factor, and the smallest power of y is y squared. So 3y squared would be our greatest common factor. What does that mean for the first term? Well, that means we can write the first term as 3y squared times 3y squared. And then the minus 15y to the third becomes a 3y squared times 5y. Again, we are after 3y squared. And then the last term is the greatest common factor, 3y squared. So we write this now as 3y squared times 1. Again, this is critical to have 1 as a placeholder. Now we can factor out the 3y squared, because each term has a 3y squared term. So 3y squared times, parentheses, 3y squared minus 5y. Remember, we're taking the 3y squared out. And here we only have 1 left, plus 1, because the 3y squared is already in front here of the parentheses. Let's check our work. 3y squared times 3y squared is 9y to the fourth. And 3y squared times minus 5y is minus 15y to the third. And 3y squared times 1 is 3y squared. So then this is our correct answer. Okay. And when we look at the next exercise here, again, we look at the coefficients, and we know that 3 is a common factor. Furthermore, xy appears in each term. So, and x, the smallest power of x is x squared, and the smallest power of y is simply y. So our greatest common factor that we need to find in each term is 3x squared y. And for the first term, we multiply it by 2, because that would be 6x squared y. And here, when we factor out 3 out of 21, we get a 7. So 3x squared y times 7, and we have a y. Because when we multiply these two monomials, we get 21 with a minus 21, and x squared, we need another x here, times 7xy, again that's 21 with a minus sign, and x squared times x is x to the third, and y times y is y squared. And then for the last term, we have 3x squared y times y squared, because 3x squared y times y squared is 3x squared y to the third. So then our final answer is when we take the greatest common factor of 3x squared, becomes 3x squared, parentheses, 2, that's this 2 here, minus 7xy, minus 7xy, and then plus a y squared. That is y squared here, because we factor out the 3x squared y of each term. So this then is our final answer. 3x squared times 2 minus 7xy plus y squared. And so it gets more interesting as we look at the various examples. So when you look at the coefficient of 30 and 50, you notice that 10 is a common factor. So we can write this as the greatest common factor 10. And a is common to each term. The smallest power of a is 6, so 10a to the 6. And b is a common factor, and the smallest power of b is b to the 4th. And c is a common factor, and the smallest power of c is 5, so c to the 5th. So then for the first term, we would have to have a 3, so that 10 times 3 is 30, and we have an a to the 6, so inside the parentheses we need an a squared, because then a squared times a to the 6 is 8 to the 8th, and we have b to the 4th and c to the 5th, that's already the lowest ones, so minus, and when we factor 10 from a 50, we get a minus 5. And so a to the 6 is already the greatest common factor, b to the 4th, but here's a b to the 5, so what we, or let me rewrite this as a whole expression. So minus, here's our greatest common factor. And so we had a to the 6, and that's already a factor, b to the 5th, but we have a b to the 4th as a factor, so it means we need a b here. And then c to the 11th, but we have a c to the 5th already here rather, so it'd be c to the 6th. And you can see when we multiply these numbers together, we get 10 times 5 is 50 with a minus sign, and 8 to the 6 is 8 to the 6, and b to the 4th times b is b to the 5th, and c to the 5th times c to the 6th is c to the 11th. So now when we take out the greatest common factor of 10, a to the 6th, b to the 4th, c to the 5th, then inside the parentheses goes the 3a squared, 3a squared, minus, that's the last term, so the minus sign comes from this one expression here, minus 5bc to the 6th, minus 5bc to the 6th power. And again, we can check our work. 10a to the 6th, b to the 4th, c to the 5th times 3a squared. 3 times 10 is 30. That's what we started out with. And a to the 6th times a squared is a to the 6th, a to the 8th rather. And we have a b to the 4th, and we have a c to the 5th. So then for the second term, minus 5 times 10 is minus 50. And we have an a to the 6th here. And b to the 4th times b is b to the 5th. And c to the 5th times c to the 6th is c to the 11th. So we can be confident that this is the correct factorization then. The next two exercises are very similar, except we are asked to factor with a negative coefficient. So this is a negative 8. So we have already negative coefficient there. So negative 8 times x. And so to make that a negative number, we have to write that as minus 8 times minus 4. So now when we take out the minus 8, we wind up with minus 8 times x minus 4. So again, we can check our work. Minus 8 times x is minus 8x, and minus 8 times minus 4 is positive 32. And in a similar way, number 7, so 3 is a common factor to each term. So then we have a minus 3 times x squared. And we have a minus 3 times 5x, because minus 3 times 5x is minus 15x. And we have a minus 3 times the minus 3, because we know that minus 3 times minus 3 is positive 9. So now, by taking our negative coefficient, minus 3, from each term, we write that in front of the parentheses, minus 3, and inside the parentheses goes the x squared and the 5x. And the negative 3. Again, let's check our answer. Minus 3 times x squared is minus 3x squared, which we started out with. And minus 3 times 5x is minus 15x, so that works. And minus 3 times minus 3 is plus 9. So this is our correct factorization with a negative coefficient. So let's apply what we have learned to an application here. And so mathematics is very often used for modeling certain things. And so in this example, we look at the model of the height of a softball. And suppose a softball is thrown upward with an initial velocity of 64 feet per second. Its height h in feet after t seconds is given by the function h of t equals minus 16t squared plus 64t. And when you graph this function, it looks like this. So here the ball is thrown upward, and here we show the height as a function of time. So h of t is minus 16t squared plus 64t for t between 0 and 4, 0 and 4 being included in this. So if you want to know how high the ball is after 2 seconds, then we just go to 2 seconds, and the function value is about 64 or something. So we'll see. Anyway, the first question is, the A question is, given this function for the height as a function of time, we are asked to find an equivalent expression for h of t by factoring out a common factor with a negative coefficient. So let's think about that. And we notice that both 16 and 64 have a common factor of 16. So in other words, we can write h of t as minus 16 times t squared. And 16 goes into 64 4 times. So now we have it as minus 4t. Minus 16 times minus 4 is part of 64. And then there's a t. So that would be the answer for part A. It's really just applying what we've learned in the previous examples. And then check factoring by valuing both expressions for h of t at t equals 1. Okay, so what is t of 1? Or h of t equals 1? So h of t equals 1 means h of 1. We replace every t with a 1 in the original expression. So that means minus 16 times 1 squared minus, rather plus 64t or 1. So that means it's equal to minus 16 plus 64, and that would be 48. And so the height would be 48 feet after 1 second. Now we're replacing t with 1 in the factored expression, using the factored expression for h of t, which was minus 16 times t squared minus 4. Well, here's a correction, by the way. The factored expression should read minus 16t times t minus 4, because t is a common factor. So minus 16t would be the greatest common factor. So minus 16t, and t is equal to 1. Well, so 16 times 1 times t minus 4, so 1 minus 4. So that gives us minus 16 times 1 minus 4 is minus 3. And minus 16 times minus 3 is equal to positive 48 feet. So, of course, in both cases, the answer should be the same, whether it's factored or not. And so then we can also look at it on the graph. And on the graph, there's a little hint here for t equals 1 second. So here we go until we meet the line, the graph. And we notice it's a little below 50, so 48 makes sense graphically. And it certainly shows us numerically, analytically, that the height of the ball is about 48 feet. Okay, so that's the so-called mathematical model of the flight or the height of a softball. And again, it's only a model. The reality is a little bit different because there are a couple of factors that are being neglected here. One would be the drag on the ball and the weight of the ball and so on. But anyway, it's a pretty good model. So anyway, that's what answered the questions here. The next concept is factoring by grouping. And as I mentioned in the beginning, in the introduction, that's a very important concept because we'll be using it all the time when we're factoring polynomials using the AC method. So here's an example of what it looks like. Here we have an expression a minus b times x plus 5 plus a minus b times x minus y squared. So the question is, what is the greatest common factor here? And so far, the greatest common factor has always been a monomial. In this case, the greatest common factor is a binomial, a minus b. In other words, that's a factor common to both terms. So we can factor that out. And so if you write it this way, then it becomes an a minus b. And then inside the parentheses, we have an x plus 5 and an x squared, x minus y squared. That's inside the parentheses. If you do it in reverse, you multiply a minus b times x plus 5, you get a minus b times x plus 5, and you get a minus b times x minus y squared, so what we started out with. So now all we need to do is simplifying the expression inside the brackets. We drop the parentheses because they're both preceded by plus signs, so we don't need to do anything extra. So then that becomes a minus b times, and then x plus x is 2x, and there's a 5, and there's a minus y squared. So that is the factorization of this expression here. And here the greatest common factor was a binomial, and that's different. And that's one of the key observations when it comes to factoring by grouping. So we'll be doing some of the examples of factoring by grouping. And again, we'll be using that concept quite a bit in the future. So when we have something like this, when we have 4 terms, in many cases, we can factor by grouping. And the way it works is we have one group here, and we have another group there. That's why it's called factoring by grouping. You look at the first group, and to find the greatest common factor, by now you probably can already notice what that is, it's y to the second power. So y to the second power, when we factor that out from the first group, then it leaves us a y here and a 3. And what's so nice about factoring by grouping is that if you have the binomial for the first group, you know it's going to be the same one for the second group, y plus 3. So now we just have to ask ourselves, what do we have to factor out from the second group? What's the greatest common factor? Well, you probably notice it's equal to 4, so plus 4. And sure enough, if we check that, 4 times y is 4y, and 4 times 3 is 12. When you look at this expression, what is the greatest common factor? Well, it is y plus 3. So therefore, we can write this as y plus 3 times, and now the y squared goes in here, plus the 4. And this is the factorization of this expression of this polynomial here. So this is y squared plus 4, y squared plus 4 times y plus 3. Again, you can go through reversing this, multiplying these polynomials together, and you will get this expression here. So you may want to think about what happened here, that you can recreate that in your mind, what we did here. So from the first group, we factored out the y squared, because that was common to both terms. That left us with a y plus 3. And again, once you know the first binomial, it'll be the same for the second group. So that tells us we need to factor out a 4 rather. And then y plus 3 is our greatest common factor. And in the other set of parentheses, and by the way, that's multiplication, we put the y squared and we put the 4. So we do it a few more times, or at least one more time, and then you probably get the idea how this all works. Now, sometimes we need to rearrange things a little bit so we can factor by grouping, and so we have a common factor here. For example, we notice that 4 and 20 are common factors because 4, of course, is a factor by itself, but 4 is also a factor of 20. Similarly, 3 and 15, there's a common factor of 3 in both of them. Here it's a factor itself, and here it's 3 times 5. So now we just need to rewrite this expression. So when we rewrite this as 4x to the third plus 20x squared minus 3x minus 15, and we look at these two groups, the 3, first group, second group, then for the first group we know we can factor out a 4 for the coefficients, and we can factor out an x squared. Again, it's the lowest exponent for x, lowest value. So that means in the parentheses we need to write an x, because 4x squared times x is 4x to the third, and we have to have a 5 when we factor out a 4x squared out of 20. And so we know this binomial is the same one as for the first one, for the second group, so x plus 5. So it becomes clear that we need to factor out a negative 3, because then minus 3 times x is minus 3x, and minus 3 times positive 5 is negative 15. And in this expression, we notice that x plus 5 is the greatest common factor. So let's write that down here. So x plus 5. And then what we do is we put another set of parentheses here indicating multiplication. We write down the 4x squared here and the negative 3 there. So this then is the factorization. So that's equal to 4x squared minus 3 times x plus 5. And remember that's implied multiplication. And one more example here. Here we look at the first group, and here's the second group. And we notice that we can, the greatest common factor is x, and the greatest common factor is x squared. So that means for the first set of parentheses, we need to have an x, so that x squared times x is x to the third. And then we need a 5, because x squared times 5 is 5x squared. So now we know what the binomial expression is like. It's x plus 5, almost like in the previous example. So we need to factor out a 4. But now we notice that that's not going to work, because 4 times x is 4x, and 4 times 5 is 20, but we need a minus 20. So in other words, factoring by grouping is not going to work. Cannot be factored by grouping. So that can happen too. Not all expressions with 4 terms can be factored by grouping. So in conclusion, I would just highly recommend you do additional drill exercises for factoring by grouping, because you really need to know how to do this. It's a required skill. Otherwise, factoring trinomials and similar expressions is going to be very, very difficult if you don't master factoring by grouping. That's a real basic skill. Okay, so that concludes this section 4.3.